So here's an example of trying to find the complex zeros of a polynomial function. And I took this right from the practice test for this exam number 3, and it's going to be question number 4. However, the questions do vary depending on person, so the numbers might be different, but I can at least show you the general process as I've explained it. This is a 3, so this is a 3rd degree polynomial. So that means that it should have 3 zeros at the most. And so what I need to do first is find one rational, real zero. So I'm going to start by listing all of my potential rational zeros. And that's done by making a list of all of your possible p's over your q's. So remember, p is found by taking all of the factors of the very last term, the constant term, and 26 actually has quite a few. So 26 and 1, 2 and 13, maybe not quite a few. I think that's it. Let's see, is 26 divisible by 4? No, okay, so those are all my p's. My q's are actually pretty easy because the leading coefficient here is just a 1. So the only factors of 1 are 1. So putting that together, creating my list of potential p's over q's will look like this. Plus or minus 26 over 1, which I don't have to write, plus or minus 1 over 1, 2 over 1, and 13 over 1. All of those plus or minus. Okay, sorry, my phone rang and I got interrupted. But these are all of my lists of potential rational zeros, p over q. So what I need to do now is I need to test each of those zeros until I find one that actually is a zero. So that means that on my list there are 1, 2, 3, 4 different values, but I have to take both the positive and the negative into consideration. So that leaves 8 possible zeros that I have to test, and sometimes unfortunately you end up testing 7 of them before one of them works, but eventually something should work. So we're going to test each of those zeros, and there are 3 ways to test. So you don't have to do all 3, you just pick one way, but I'll show the 3 different ways. So the first way to test is what's called doing f of a. And if f of a equals 0, then it is a 0. So I'll start with, let's say, the number 1. So my test value here is going to be a equals 1. I want to see if 1 is a 0 of this function. So what I can do is I can take my original function, f of x, and I can plug 1 into that function. And I chose 1 just because it's easy to plug in. 26, the numbers get a little bit big. Okay, so plugging everything in, 1 cubed is 1, 1 squared is 1, then multiply that by 8, 25 times 1, and then minus 26. Let's simplify all of this and see if it comes out to be 0. So this is negative 7 when I combine the first 2 terms. When I combine the second 2 terms, I get negative 1, so that's a grand total of negative 8. So, no, that is not a factor, not a 0. Okay, so I would continue to do that until I've tested all 8 potential zeros. However, there are other methods to test as well, so here is another one. Let's say this time I want to test negative 1. And so one of the other ways to test is to actually divide. So I could divide my f of x, my original function, by the factor that corresponds to the 0 that I'm trying to test. And if negative 1 is the 0, then x plus 1 is the factor that corresponds to that. So I want to divide those out. And if it is a 0, then the remainder will equal 0. Okay, sorry about that, got interrupted again, but let me continue. We're looking to see if the remainder is 0 when you divide those two factors. So in terms of doing that division, let me switch to another sheet of paper and show you what that would look like. So dividing f of x, which looked like this, x cubed minus 8x squared plus 25x minus 26 by the factor that we're testing, x plus 1. So there are two ways that you can do this division. We can use the long division method, or we can use the synthetic division method. They both work equally well. It's just a matter of how you're more comfortable dividing. So if I'm doing long division, I'm going to keep all of my variables, not just the coefficients with the variables, and I'm going to divide that way. And it's going to be set up to look like that. Or if I'm doing the synthetic division, I'm just going to take the coefficients of each term and divide it by the factor x plus 1. Now, some people do it where they subtract the terms. Some people do it where they add the terms. Everybody's got a little bit of a twist on how they do it, so it doesn't have to look exactly like this. But in general, you need to have some method that works. And I'm going to continue to divide. And let's see. Okay, so in my division, what I'm looking for is my remainder, which is the very last term of my division. Or if I've done long division, whatever your remaining term down at the bottom is, that's what you're going to look at. Now, regardless of the method that you choose, you should get the same result when you divide. You should get the same remainder. And in this case, since that remainder does not equal 0, then this is not going to be a factor, or not a 0, meaning the same thing. Hopefully I didn't make any mistakes here. I was going kind of fast, and it's hard when you're talking and writing at the same time to make sure that your math is correct. But in general, that's what the process looks like. So far we haven't found any zeros. We've tested 2 of the 8 possibilities. And remember, these A's, B's, and C's that I'm showing here, these are 3 different options. You don't have to use all 3. You just pick the one method that you think works best. And generally, this last method, if you're allowed to use your calculator, it is the fastest way to do it. What I'm going to do is type that function into my graphing calculator, x cubed minus 8x squared plus 25x minus 26. And I'm going to take a look at the graph. Remember that zeros are x-intercepts. So I want to see, where does this graph cross the x-axis? And it looks to me like it's crossing right there at 2. So x equals 2 is going to be a 0. Alright, so that is all you need, just 1 0. Step number 1 in this process is find 1 0 that works. And again, any of these methods, A, B, and C, will get you there. Clearly C was the fastest. That brings us to step number 3. Step number 3 is, once you've got that 0, you've got to divide that original polynomial function by the 0 that you know works. And again, synthetic division, polynomial long division, they both give you the same outcome. So if x equals 2 is a root, then x minus 2 is a factor. And again, this is just the way that I set it up. It is possible to do it differently and still get it correct. So let me do my synthetic division. And what I'm looking for is to make sure that my remainder is 0. That's just a way to double check that what I saw on the calculator actually is correct. But the purpose of this step number 3 is to obtain this quadratic result once I've factored out the 1 0 I know works. So right now this is the factored form of my polynomial, x minus 2 times x squared minus 6x plus 13. You could possibly factor it more depending on whether this factors here, but this is what we've got right now. So moving on to step number 4. Once I have it factored down so that I have a quadratic, I need to then solve that quadratic. So that means to set it equal to 0 and either factor, if possible, or use the quadratic formula if you can't factor. Now, quadratic formula always works, factoring only works sometimes, so that's just something to keep in mind. So I'm going to use my quadratic formula to solve this. And I'm going to do it rather quickly. And going down to simplify this even more, at the moment I know I've got a negative inside of my square root, so that means that I'm going to have complex roots, which matches up to what the directions asked us to do, find the complex roots. The square root of negative 16 is equivalent to 4i, and then if everything's divisible by 2, then I can go ahead and do that. So, remember, this is a third degree polynomial. If it were fourth degree, it would work a little bit differently. I'd have to repeat some steps, and I'd get a different number of zeros. But basically, I have one real 0, which we were able to find on the calculator at x equals 2, and then I have two complex zeros, which are conjugates, 3 plus 2i and 3 minus 2i. And because of the fact that it was a third degree polynomial, the most number of zeros that I could have is 3, and that's how many I found. So I'm now done with this problem. Hopefully that helps.